Plastic waste is piling up in the world's landfills, sewer systems, and in the ocean.
A gigantic swell of trash floating in the Pacific Ocean.
We see plastic everywhere.
Stretching across the open ocean, plastic waste drifts with currents, creating a crisis few can see.
Plastic pollution is destroying life in the ocean.
American engineers are confronting this invisible enemy with innovative systems that locate, collect, and recycle millions of tons of debris.
A collection bag we call the retention zone. It looks very small, but actually it's 5 times the length of a school bus.
From floating U-shaped barriers to AI-driven tracking, their approach combines science and ingenuity. The scale is massive, the challenge relentless, yet their results reveal that even the middle of the ocean can be reclaimed from humanity's plastic footprint.
I believe Great Pacific Garbage Patch can completely clean itself in just 5 years.
The ocean plastic crisis. Scale, hotspots, and why it matters. Trillions of pieces of plastic drift across the world's oceans, hidden in plain sight. They gather in 5 massive garbage patches, with the largest stretching between Hawaii and California. The Great Pacific Garbage Patch is often described as twice the size of Texas, holding roughly 1.8 trillion pieces of plastic and over 100 million kilograms of waste.
In the ocean, at various depths, so it's not as if you can stand on this garbage patch. It's not an island of garbage.
This is not a solid island. It is a floating soup of plastic, where large pieces make up nearly 92% of the mass. The rest are fragments, breaking down slowly, almost invisibly, into microplastics that weave themselves into the ocean's currents. These tiny shards find their way into the food chain, carried by fish and shellfish, ending up on plates across the globe. The impact on wildlife is profound. Over 900 species are known to ingest or become entangled in plastic. Sea turtles mistake drifting bags for jellyfish. Birds feed their young bits of plastic, mistaking them for food. Even the tiniest fish carry traces of plastic in their systems, and that pollution climbs steadily through every level of the marine ecosystem. Beyond the immediate harm, plastic interferes with the ocean's ability to trap carbon, a subtle but serious effect on climate balance. Scientists needed to understand the problem before tackling it. Expeditions ventured into the Great Pacific Garbage Patch, documenting the scale, density, and movement of the debris. Every sample and observation revealed a new piece of the puzzle, showing how plastic behaves in ways that make it nearly impossible to contain without careful planning. This research led to the first designs for cleanup systems, machines built to drift with the currents while capturing concentrated plastic. Every detail mattered, from the angle of barriers to the speed of currents, because even a small miscalculation could allow plastic to slip past. The ocean plastic crisis is immense, overwhelming, and quietly relentless. But mapping it, understanding it, and developing tools to remove it revealed a path forward. Science began to turn observation into action, showing that even a problem of unimaginable scale could be tackled when approached with precision, creativity, and relentless determination. The ocean may seem endless, but every piece of plastic collected is proof that action matters and that the tide can change. Early exploration. In 2015, the ocean cleanup launched the Mega Expedition, sending 30 vessels and more than 650 surface nets into the Great Pacific Garbage Patch.
By September 2015, we completed the Mega Expedition. We got all our samples in.
The mission collected over 1.2 million plastic samples, each piece a fragment of a crisis that had grown beyond imagination. That same year, the multi-level trawl expedition probed deeper, measuring plastic down to 5 meters. Most of it stayed near the surface, drifting with the currents, waiting for someone to notice. These expeditions revealed patterns that were invisible from the shore. Plastic did not cluster randomly. It moved in swirls, forming pockets of concentration in the endless blue. Every discovery exposed just how clever and persistent this pollution had become, blending into the ocean while quietly reshaping the ecosystem. The data painted a map of danger and opportunity. Scientists now understand where the plastic gathered, how it flowed, and which areas were most affected. It became clear that simply picking up plastic in one spot would never be enough. Engineers needed to design systems that could cover immense areas, adapt to shifting currents, and capture debris before it broke down into microplastics. Each piece of plastic collected told a story. Some were fragments of fishing gear tangled in the lives of seabirds. Others were bottles and containers that had traveled thousands of kilometers, carried by wind and tide. By analyzing these samples, researchers could trace the sources, learning which regions of the planet contributed most to the mess. The scale of the challenge became tangible, but so did the chance to fight it. With precise maps of distribution and knowledge of how plastic behaved in the gyres, engineers began crafting technology to confront the problem. Barriers, collection systems, and moving platforms were designed to catch plastic efficiently without harming marine life. What started as exploration turned into action. The ocean, once a hidden battleground, was now charted. Solutions were no longer theoretical. Early expeditions revealed a truth few could see from the shore. The plastic was everywhere, and its paths were predictable. Mapping it turned chaos into a strategy, giving humans a chance to reclaim what the waves had quietly stolen. The next step was to act, to build, and to prove that even the most immense and mysterious pollution could be confronted with ingenuity and persistence. The birth of the ocean cleanup. In 2012, Boy and Slat stood on a TEDx stage and proposed something almost unimaginable: use floating barriers to trap and remove plastic at a massive scale. It was an idea so bold that many dismissed it, but it sparked a movement. By 2013, the Ocean Cleanup nonprofit was born, dedicated to tackling the legacy plastic that had silently accumulated across the world's seas. The mission was clear from the start. This was not about short-term fixes or symbolic gestures. The aim was to engineer systems that could scale, capturing vast amounts of plastic while leaving marine life undisturbed. Every design decision balanced efficiency with ecological responsibility. It was a challenge that required thinking far beyond conventional engineering, demanding creativity, patience, and a willingness to test the unknown. From concept to prototype, the journey was relentless. Early designs were tested in small lakes and controlled environments to understand how plastic moved in real currents. Engineers observed how barriers reacted to waves, wind, and debris. Every failure became a lesson, revealing flaws that might have been invisible on paper. Adjustments followed, improving strength, flexibility, and collection efficiency. By the time the first sea trials began, the team had combined data from ocean expeditions with innovative engineering. Barriers were no longer theoretical lines in the water. They became living structures, designed to drift with currents while guiding plastic toward capture points. Sensors, floats, and mooring systems worked together, allowing the system to operate autonomously over months at a time. The ocean cleanup team understood that the oceans were unpredictable. Storms, currents, and debris could undo months of work in minutes, yet every challenge was met with iteration and ingenuity. Prototypes were tested, retrieved, and refined repeatedly, each cycle bringing the vision closer to reality. The project was as much about understanding the ocean as it was about removing plastic. From a single idea on a stage to vessels moving quietly across the Great Pacific Garbage Patch, the ocean cleanup transformed a radical concept into a tangible mission.
As they begin to deploy teams and ocean cleanup systems to the Great Pacific Garbage Patch.
It was a marriage of science, engineering, and determination, driven by the understanding that the oceans held both the problem and the solution. Every system deployed became a statement. Even the most massive, mysterious pollution could be confronted when human ingenuity was applied relentlessly. The dream of removing plastic from the world's oceans had moved from imagination into action, and the first real tests at sea were only the beginning. Prototyping at sea. System 001 slipped into the Pacific in 2018, a long floating line against an endless horizon. It was the first real test of a barrier-based cleanup system, sent off the United States West Coast to see if theory could survive the ocean. The trial did not capture large amounts of plastic, but every hour in the water revealed lessons no laboratory could provide. Currents pushed the barriers, waves tested their durability, and small fragments of plastic offered hints on how the system could guide debris more effectively. Engineers pored over the data. Every flaw became a point of focus. Adjustments were made, and System 001 evolved into System 001B. Changes improved stability, capture efficiency, and the ability to withstand the unpredictable conditions of open water. The ocean is unforgiving, but the team learned how to make the system resilient. These iterations were slow, methodical, and filled with moments of doubt. The ocean refused shortcuts, demanding solutions that worked in practice, not just in theory. System 002 followed, a refined design built from all the knowledge gained in previous trials. By 2021, it finally began harvesting measurable amounts of plastic. Small at first, then increasingly larger loads, it proved that the concept could function in the real world. Every netted fragment became proof that persistent, careful engineering could confront the vastness of the ocean. The prototypes taught more than mechanics. They revealed how plastic behaves when caught in a moving system, how currents funnel debris into concentrated areas, and how seasonal shifts affect collection efficiency. Each test turned raw data into strategy, informing the placement, shape, and operation of future systems. The ocean still hid dangers and surprises, but understanding them allowed humans to fight back. By the time System 002 proved itself, the focus shifted from testing to real extraction. Engineers could finally scale the operation, sending multiple units into areas where plastic had accumulated for decades. The experiments at sea were no longer isolated trials. They became the blueprint for the first fully operational cleanup campaign. Prototyping at sea transformed a bold idea into tangible action. The barriers moved from concept to reality, from theory to functioning machines navigating the currents, learning from the ocean itself. Each success, each small capture built momentum. It was a step closer to confronting a crisis that had seemed impossible, a proof that the right combination of knowledge, persistence, and ingenuity could begin to reclaim the seas. Engineering scale-up. System 03 entered the Pacific quietly, a massive structure stretching over 2 kilometers across the waves. Its U-shaped floating barriers, paired with subsurface skirts, funneled plastic into a central retention zone. This was no longer an experiment. The system was built to operate at scale, drifting with the currents, guided by careful modeling that pinpointed hotspots where debris gathered. Vessels towed the barriers across the Great Pacific Garbage Patch, each movement precise, each deployment based on months of data and observation. The ocean still had its surprises, but System 03 could adapt, bending with the waves and holding firm against storms. Every barrier acted like a trap laid out across invisible highways of plastic, catching fragments that had floated unchallenged for decades. By 2025, these systems had removed millions of kilograms of plastic. Small pieces, bottles, nets, and containers all trapped within the floating corridors, collected and held. Each haul was evidence that large-scale cleanup was possible, that the ocean could be confronted with a methodical approach. The goal was ambitious: to remove 90% of floating ocean plastic by 2040. Every success, every ton collected, brought that vision closer to reality. Operating at this scale revealed hidden lessons. Some debris proved heavier than expected, dragging skirts deeper and requiring adjustment. Seasonal shifts created new currents, sending clusters of plastic into uncharted paths. Engineers learned to predict these changes, tweaking deployment schedules and positioning to maximize efficiency. It became a constant interplay between human planning and the ocean's own rhythms, a dance that demanded attention and respect. The scale of the operation also opened new opportunities. Once collected, the plastic no longer remained waste. It became material that could be repurposed, from recycled goods to construction materials, closing the loop and turning decades of pollution into a resource. The mission extended beyond cleanup into innovation, showing that even the most entrenched environmental problems could be transformed when approached creatively. System 03 and the operations that followed proved that the ocean could be mapped, understood, and acted upon. Large-scale extraction moved from theory into daily reality, and the once invisible plastic soup began to shrink. every barrier deployed, every kilogram recovered was a reminder that even the vastness of the ocean could be confronted with ingenuity, persistence, and careful design. Extracting plastic was only the beginning. The next challenge was turning what had once been a threat into something valuable, reshaping the problem into a solution. Recycling ocean plastic. The plastic pulled from the ocean does not come clean or ready to use. It drifts for years, tangled with fishing nets, ropes, and debris weathered by sun, salt, and waves. Sorting it is painstaking. Cleaning it requires careful attention, separating what can be reused from what remains too degraded. Every fragment tells a story of a journey that spanned thousands of kilometers, carried by currents, invisible to most of the world. The ocean cleanup works with partner companies to transform this recovered material into something functional, something durable. Early efforts produced sunglasses, a simple yet powerful symbol that ocean plastic could be given a second life. These first products proved that waste collected from the vast Pacific was not just debris, but a resource waiting to be reimagined. Each piece carries the mark of the ocean, yet becomes something people can hold, use, and see as valuable. The innovation did not stop there. Partnerships expanded to create limited edition car trunk liners, strong and practical, made entirely from recycled ocean and river plastic. Even a music album was pressed using the material, blending creativity and sustainability in a tangible form. Each product served as a reminder that the problem of plastic is not permanent if approached with determination and ingenuity. Recycling ocean plastic also revealed hidden challenges. Material from different sources varies in composition and quality, requiring unique processing methods. Contaminants must be removed, textures adjusted, and durability ensured. Every batch of recycled plastic demanded problem-solving, experimentation, and careful monitoring. It was a learning process as much as a technical operation, blending science, engineering, and design into a single mission. Beyond creating products, the work has a larger purpose. Recycling proves that recovery is possible, but it also highlights the need to stop plastic from entering the oceans in the first place. Extracting and transforming what already exists is one step, but preventing new waste is essential. Collection, reuse, and reduction together form a full-circle strategy, turning a decades-long crisis into an opportunity for change. The journey from ocean to product shows that even something as vast and untouchable as the Great Pacific Garbage Patch can be confronted. Each kilogram transformed is a statement that pollution can be addressed. Every recycled piece, from sunglasses to album pressings, carries hope, evidence that human innovation can reclaim what was once lost to the waves. Stopping the flow. Studies estimate that roughly 80% of ocean plastic originates from about 1,000 major rivers worldwide. Each river is a conveyor belt, silently delivering waste that most people never see, feeding the problem far from sight. The ocean cleanup turned its attention to these invisible routes. They designed solar-powered interceptors that float with the current, using the river's own flow to funnel debris onto conveyor belts. Once on board, the plastic is captured and stored, keeping it from ever reaching the sea. Each unit can remove up to 50,000 kilograms of waste every day. The scale is astonishing. A single river can produce more plastic than most people imagine. Yet these systems turn the current into an ally, using natural energy to fight back against pollution. Since their deployment, over 20 million kilograms of river plastic have been intercepted. Bottles, bags, nets, and fragments of forgotten containers are taken out of circulation before they join the massive floating garbage patches offshore. Every kilogram captured represents plastic that will no longer drift across thousands of kilometers of ocean, entangling wildlife or breaking down into microplastics. The interceptors operate quietly but relentlessly, a presence that most people along the riverbanks never notice. They work day and night, powered only by the sun, converting a constant flow of waste into collected material ready for recycling. This method complements offshore cleanup efforts, creating a chain that starts on land and continues into the ocean. Rivers are no longer just pathways for pollution. They have become a front line in a global cleanup strategy. The broader impact is more than just numbers. Each interception is a lesson in how human ingenuity can harness natural systems to solve enormous problems. By acting at the source, the ocean cleanup ensures that less plastic ever reaches the gyres, reducing the burden offshore and protecting marine life before damage occurs. Stopping plastic in rivers transforms the flow of waste into a flow of possibility. Interceptors redirect what was once a hidden threat, turning relentless currents into tools of change. Every kilogram captured, every river cleared, is proof that even the paths we take for granted can be transformed into mechanisms for hope. The battle begins far from the ocean's vast expanse, in the quiet, powerful rivers that feed the seas. Data, AI, and precision engineering. Smart cleanup through data, artificial intelligence, and precision engineering is not just about finding plastic. It is about transforming how decisions are made across complex ocean operations. At this stage, technology acts as a coordination layer that connects prediction, planning, and execution into a single operational flow. Each element supports the next, creating a system where uncertainty is reduced and outcomes become more reliable. Advanced technology integration allows cleanup teams to move from static planning to adaptive operations. Artificial intelligence models process continuous streams of environmental data and translate them into clear operational signals. These signals inform when to deploy, where to concentrate effort, and how long systems should remain active in a given area. Instead of fixed schedules, cleanup strategies become flexible, adjusting as conditions evolve. This adaptability is critical in dynamic marine environments where small changes can have large downstream effects. Precision engineering ensures that digital insights translate into physical performance. Collection systems are engineered to respond accurately to AI-generated instructions, maintaining stability and efficiency even in challenging conditions. Sensors embedded within the equipment monitor performance metrics such as load balance, flow rates, and structural stress. This feedback allows engineers to fine-tune operations in real time, reducing downtime and preventing avoidable failures. The result is a tighter alignment between prediction and execution. The value of this approach becomes especially clear when viewed through the lens of efficiency. Research indicates that optimized routing and intelligent guidance systems can increase plastic recovery rates by more than 60%. These gains come from reducing unnecessary movement and maximizing productive operating hours. Fuel consumption declines, mission durations shorten, and crews can focus on oversight rather than constant manual adjustment. Over repeated deployments, these efficiencies compound, strengthening long-term operational viability. Another advantage lies in risk management. By predicting debris concentration zones more accurately, teams avoid deploying equipment into low-yield or hazardous areas. This reduces exposure to severe weather, minimizes wear on machinery, and improves safety for crews. Data-driven planning shifts cleanup work from reactive problem-solving to controlled execution, which is essential for scaling operations responsibly. Despite these technological advances, their influence reaches a natural limit without broader alignment. While engineers continue refining extraction tools and recycling pathways, real-world impact also depends on supportive policy frameworks and industry participation. Technology can guide and accelerate progress, but meaningful change requires adoption beyond engineering teams and into the systems that govern production, waste, and accountability. Driving a circular plastic economy. Industry and policy play a decisive role in turning ocean cleanup from a corrective effort into a long-term solution rooted in a circular plastic economy. While recovery systems remove waste from the environment, it is industry adoption that gives that recovered material lasting value. When businesses actively use recycled plastics, they help close the loop between cleanup, production, and consumption. Private sector engagement has become one of the strongest drivers of this shift. Global brands such as Adidas and Patagonia have incorporated ocean-derived plastics into footwear and apparel lines. By doing so, they demonstrate that recycled polymers can meet high performance and durability standards. This visibility changes perception across the market. Recycled plastic is no longer seen as a compromise, but as a viable and desirable material. As demand grows, investment in collection, sorting, and processing infrastructure becomes more attractive, reinforcing the economic case for cleanup. This market pull is further strengthened by coordinated policy action. The proposed Global Plastics Treaty represents an effort to address plastic pollution at its source by reducing excessive production and improving waste management worldwide. By setting shared targets and accountability frameworks, the treaty aims to create stable demand for recycled materials while discouraging reliance on virgin plastic. For cleanup initiatives, this policy supports matters because it ensures that recovered plastic has a clear pathway back into the economy rather than returning to landfills. Together, industry commitments and policy frameworks help shift responsibility upstream. Companies are encouraged to design products with end-of-life recovery in mind, while governments create conditions that reward circular practices. This alignment reduces future leakage into oceans and increases the value of material already collected. Yet even as industry participation expands and policy momentum builds, the sheer scale of plastic already present in marine environments cannot be ignored. Progress is real, but the challenge remains vast. Understanding this balance between momentum and magnitude leads naturally into a final reflection on what long-term success truly requires. The road ahead: ambition, limitations, and hope. The road ahead for large-scale plastic recovery is defined by ambition tempered with realism and sustained by cautious hope. Current milestones show that progress is no longer theoretical. Millions of kilograms of plastic have already been removed from ocean systems and heavily polluted rivers. These achievements demonstrate that coordinated action, engineering innovation, and long-term commitment can produce measurable results. What once seemed impossible has moved firmly into the realm of demonstrated capability. Equally important is what happens after plastic is recovered. Early recycled products made from collected material have proven that extraction efforts can support a functioning circular economy. This step confirms that recovered plastic does not have to be treated as waste with no future value. Instead, it can be transformed into usable materials that re-enter global supply chains. This connection between cleanup and reuse gives environmental action economic relevance, which is critical for long-term continuity. Looking forward, future goals remain bold. By the year 2040, engineers and organizations aim to eliminate up to 90% of floating ocean plastic pollution. This target reflects confidence in scaling existing technologies while improving prevention strategies that stop plastic before it reaches open water. Expansion will require more systems, broader geographic coverage, and deeper cooperation across borders. At the same time, expectations are grounded in the understanding that cleanup alone cannot address every source of pollution. Limitations remain part of the conversation. Ocean conditions are unpredictable. Plastic continues to enter waterways daily, and not all pollution can be captured efficiently. Acknowledging these constraints is not a weakness, but a sign of maturity. It allows planners to focus on realistic impact rather than symbolic success. The emphasis shifts toward reducing harm, buying time for ecosystems to recover, and preventing future damage. The importance of this effort extends far beyond visible debris. Removing plastic before it breaks down into microplastics helps protect marine life that mistake fragments for food. It also reduces the spread of contaminants through the food chain, which ultimately affects human health. Every kilogram removed represents less long-term exposure and less ecological strain. Hope emerges not from perfection, but from progress. Each milestone proves that intervention works. Each refined system improves efficiency. The road ahead is challenging, but it is no longer uncharted. With persistence, cooperation, and accountability, ambition can translate into lasting environmental recovery on a global scale. Thanks for watching. See you on the next one.